Hello, am I audible?
Yes.
Okay. Okay. So again, so we'll do a problem session on week six problems. Sorry, week six coursework. So again, the pattern will be I'll write a question. I'll give you time to think. If you have a doubt in question or the answer, you can just ask me. Okay. So let's start. Uh, Okay, so let me first give you some definitions, so which will be useful in this problem session. So first definition is of vertex cut. So we will use this definition in almost every problem, right? So let me just write the definition and then we'll see the problem. So this vertex cut is also called separating set. So a separating set or vertex cut of a graph G is a set of vertices subset of vertex set such that G minus S has more than one connected component. And also the connectivity of G. So connectivity of G. So we will denote it using this sort of K of G is the minimum size of a vertex cut such that G minus S is disconnected or has only one vertex. Okay, so here is a very simple definition of a vertex cut. So let me give you an example and then it will be clear. So let's say we have a graph G which looks something like this. So let me name vertices. Let's say A, B, C, D, and E. So in this graph, for example, if you take S as B comma E, and if you look at G minus S, the graph would look like this. B and D, let's say, it will look at A, C, and E. So if you see, uh, if I take set S, right here as B comma D, and if you delete the vertices B and D, clearly the graph that remains is just three isolated vertices. So basically it contains three connected components, right? So this is one connected component, this is one, and this is one. So there are three connected components. So in this case, we say S is a vertex cut. So we say, sorry, so we say that S is a vertex cut. Now, is this smallest size vertex cut? Can you see in this example and check if there is a vertex cut of size less than 2?
If we cut only E, then
Okay, so let's try. If you cut on E, so let's say I deleted vertex E, I'll be left with this graph. So how many connected components are there in this graph? Only one, right? So this whole thing is in one connected component, right? So that means E is not a vertex cut. So again, if you observe, uh, there is no vertex cut of size 1 because every vertex is in some cycle, right? So a vertex that is inside cycle cannot be a cut vertex. So that you can observe this This is just a simple observation. So here again, since every vertex is inside a cycle, if we remove only one vertex, then the graph will remain connected, right? So that means, in fact, okay, the s that I have deleted is of smallest size, right? So for this graph, the connectivity is 2. So we denote it by this, k of g is equals to 2, because s is the minimum size of a vertex cut, right? So for this graph, the connectivity is 2. Okay, so now let me also put one more line. So let me write here. So we say, so a graph is k connected if its connectivity is at least k. So take this example of a graph G. Is this graph one connected? So here is a this is just a notation, but I think since I'm going to use it over and over again in this session, so I need you to understand when do I call graph k connected. So my first question is this graph, let's say, two connected? So let's say, is G a two connected graph?
Yes.
Yes, the answer is yes. Because if so, the way at least I think about this k connected thing is that a graph is k connected is if you remove any k minus 1 edges, the graph will remain connected, right? So in this case, so if you see this graph G that I'm talking here, if I remove k minus 1 vertices, so if you see here, I have given k is equals to 2, that means k minus 1 is 1. So if you remove 1 or less than 1 vertices from here, the graph still remains connected, right? So here in this case, clearly the graph is 2 connected. Let me give you one more example and then we'll make sure that it is clear. So let me draw a graph. Okay, can anyone suggest me any vertex cut of this graph? Hel- Hello? Hello, am I audible? Hello?
Yes, sir. Sir,
Okay, I think I got
as,
disconnected for a minute. Let me just share the screen once again.
sir, hello.
Hello? Yes, yes.
Sir, can we give one vertex EF because you have given two to C, na?
Just a minute. Let me just share the screen so that. Okay, so here. So, okay, so everybody can see the screen, right?
Yes.
Okay. So, yes, so what you, so let me just check chat once again. So B and D. Okay, so let's me just write this down. Okay, so what is your question?
You have given two vertices C name, so
Oh,
I
okay,
will.
okay, sorry. A, B, C, D, E, F, let's say. Yes, sorry, yes. So okay, someone suggested that BD is a vertex cut. So let's see if that is true. So if I delete S from the graph G, the graph would look like this: A, F, C, and E. Right? So clearly, this graph here has two connected components. So this is one and this is two. So S is a vertex cut. Now again, the question is, can you give me a vertex cut of size 1 in this graph?
No.
No, right? Because every, yes, so I think somebody wrote it in the chat. Yes, no, because clearly if you see, if I remove A from the graph G, then the graph remains connected. If you remove B, C, D, E, F, anything, the graph still remains connected. So what will be the K of G of this graph, the connectivity of this graph?
Two.
Right? Because I cannot remove one vertex and make the graph disconnected. That means, and I can find a vertex cut of size 2 and remove it, and I'm left with two connected components. So this is a vertex cut and the connectivity will be 2, right? So now, okay, now let me give you a last example. And okay, so is this graph, let's say, one connected?
Lower is always true, no? If we prove that is two connected, then one is definitely the answer.
Yes, so that is true. If the graph is k connected, the graph is also k minus 1, k minus 2, up to 1 connected, right? So let me give you the last example here. So that is, so let's say,
Sir, any relation
uh,
between vertex, degree, and connection?
vertex degree and what?
K connection?
You mean connectivity?
Yes, yes.
Yes, there is a relation. It will come up in one of the theorems. I will write down that theorem. But for now, let me just stick to few examples and then I'll get back to that relation. Okay. Okay, so let's say here is a graph G. So now can anyone give me a vertex cut for this graph? So let's say this is a graph G. I'll keep the definition here. Um, okay, so I think that somebody wrote it in the chat. Uh, yes, A, B, and D. So if you remove A, B, and D, so let's say if I take S as A, B, and D, the graph G minus S will be basically just C. Now, here is just a sort of extreme example. If your graph is a complete graph, which means every vertex, every pair of vertices has a pair, then so if you look at the definition here, it says that G minus S has more than one connected component. So here, so G minus S has more than one connected component, uh, or so it also says that, sorry, here, or has only one vertex, right? So a vertex cut such that G minus S is disconnected. By disconnected, again, I mean has more than one connected component or has only one vertex. So in the case of complete graph, I need to sort of, so I need to add something extra in the definition, which is this: has only one vertex, because in a complete graph, there is no way you can remove vertices and get two connected components, because no matter which vertices you will have in two different connected components, there will always be an edge. So the vertex cut of a complete graph of size, let's say n, is always of size n minus 1. So in this case, this is of size 3, because this is a complete graph of size 4, right? So I hope this is clear. Um, okay. Um,
So what you
uh,
said in the last is not clear. Say in this
in
case, S is 3 and G minus S is 1. So
okay. So what I'm saying is, so what is the definition of vertex cut? The reason the definition of vertex cut has this extra line which is in this red box is for the following reason. So if I remove this line from the definition of uh, vertex cut, then what will be the definition? Uh, a size of a vertex cut such that g minus s is disconnected. So a vertex cut is something that disconnects the graph, right? So if I take a graph G and I deleted few vertices, what do I mean when I say G minus S is disconnected? That means there are at least two connected components, right? So let's say there is a component 1 and component 2. But the problem is that there are some graphs, for example, complete graph is probably this example, is where if no matter how many vertices I delete, you cannot get two connected components, right? So if you look at this graph, it contains four vertices A, B, C, and D, right? No matter how many vertices you remove, no matter which vertices you remove, there is no way the graph will be left with two connected components, right? Therefore, a vertex cut of complete graph is defined in the following way, so that if you remove like so if you remove some vertices such that you are left with only one vertex, then such a set is also called a vertex cut. So in this case, if you look at ABCD, there is no vertex cut of size 1, there is no vertex cut of size 2. But now if you remove three vertices, then I'll be left with only one vertex. And in the definition, if you see here in this red box, it says that in that case as well, I call it a vertex cut. So here, this graph, sorry, this set S is also vertex cut. Uh, is this clear? Or
Yes.
yeah. Okay. So yeah, so there are only two kind of graphs. Either it is complete graph or it is not a complete graph. If it is not a complete graph, you can find vertex cut where you have two connected components. But if it is a complete graph, no matter how many vertices you remove, you cannot really get two connected components. So you remove all but one vertex and you get basically only one vertex, and that will be a vertex cut. Okay. So now let me give one statement, which is that I think some of you already said this. So a k connected graph is also k minus 1 connected, right? So this is a simple statement because if I so if a graph is k connected, what it means is that if I remove k minus 1 vertices, any k minus 1 vertices, the graph still remains connected. Now clearly such a graph will be k minus 1 connected. Why? Because I'm only allowed to remove k minus 2 vertices. If I'm not able to break the graph using k minus 1 vertices, clearly I won't be able to do it using k minus 2 or less than k minus 2 vertices. Okay. Okay. So let me give you a graph G and ask you question. So let's say you have, let's say A, B, C, D, E, F, G, H, I, J. So let's say this is my graph G. So my first question is this graph 1 connected? So question, is the above graph 1 connected?
No.
Okay. Um, what about the rest of you? Okay, if your answer is yes, put +1. If your answer is no, put -1. Okay, I don't see any other answers.
So
Uh,
this graph is already disconnected. We cannot say this graph is connected because it has
yes,
already two components.
yes, exactly. So here the question I asked is the above graph 1 connected. What does that mean? So a graph is one connected. If so, a graph is k connected is if I remove k minus 1 vertices, any k minus 1 vertices, the graph should remain connected. So in this case, the definition is saying if I remove 0 vertices, the graph will remain connected. But this is not true, right? Because the graph is already disconnected, because I have this as one connected component and this as another connected component. So the graph is in fact not one connected. So one connected and connected is the same thing. So one connected and connected, it's same thing. So if I say a graph is connected, it means it is one connected, and if I say graph is one connected, that means it is connected. This two connected, three connected is a generalization of this idea of connectedness, right? So in this case, the graph is in fact not one connected. Okay, so what will be the connectivity of this graph G? So what is the connectivity activity that is k of G of above graph? So the definition of, no, that is true, it is not connected, but
Zero,
I'm
zero,
asking the k of G
zero,
value.
zero.
Zero, right? Because I don't need to remove any vertex and the graph will still remain disconnected. So that means k of G is zero, right? Okay. So now, um, okay, let me add a page. So here I defined a vertex cut. So in this similar way, I can also define an edge cut, right? So let me write down the definition. So instead of,
Sir,
yeah, yes, you can ask.
sir, is every graph is one connected, sir?
No. So for example, here, if you see this graph, this is not one connected, because when I say one connected, it means that, I mean, the one connected and connected means the same thing. If I remove zero vertices, the graph should remain connected. So if I remove empty set of vertices, like I didn't remove anything basically, is this graph still connected? No, right? Because I have two connected components initially only. In the graph only, I have two connected components. Then such a graph cannot be connected, or in this definition or in this notation, it is not one connected, right? So this is a example. This is an example where the graph is not one connected. Okay.
Yes, sir. And sir, in a plane, 2 points are there. That means this is a graph or not, sir?
This is a graph. Yes, yes. You,
Okay.
yeah. So for example, even if I draw just this A, B, C, D, this is a graph. If I add an edge, this is a graph. I mean, a graph is basically set of vertices and edges. Edges can be empty, even vertices can be empty, but that is called empty graph. That is not of interest. But even if there are no edges, so for example, the way I have drawn here, this graph, for example, this graph, I mean, this is a graph, first of all. Um, there are no edges, but the definition of graph never says that I need at least one edge. So this is also a graph G. This is not connected graph, or in this notation, this is not a one connected graph, right? Because there are four connected components. So I don't need to remove anything and the graph is still disconnected. So I can say that the connectivity is zero, right? Uh,
Yes,
I
sir. Thank
okay,
you.
okay. Okay, so what I was saying is, so here in the first definition, I was mostly talking about removing vertices from the graph G. So one can also talk about removing edges, right? So let me just define what is edge connectivity. So let me write here. So let's say edge, edge connectivity. So let me write down the definition. So a disconnecting set of edges is a set F which is subset of edges such that G minus F has has more than one connected component. So, and then we can say that a graph is k edge connected if every disconnecting set has at least k edges. And then finally, the way we defined vertex connectivity, I can also define the edge connectivity. So the edge connectivity of G. So we will denote it using K prime G. K prime of G is the minimum size of a disconnecting set. Okay. So so here is an example. So let me start with few examples. So again, so let's understand this edge connectivity definition through an example. So let me give you an example of graph G. So let's say right here. Let's say I have A, B, C, I have D, E, F. Let's say there is an edge G, H, I. Okay, can anyone suggest me a edge cut? Okay, so let me denote it by F actually. Let's say here is a graph G. Can you give me an edge cut? Any edge cut?
CH,
Okay, so let me write down CH,
DF,
DF,
DE.
CH, DF, DE. Okay, CH, DF, DE. Okay, so he basically says delete these edges. So clearly, if you see here, this is a disconnecting set of edges because if I delete this red, so if I delete this three edges, I get two connected components. One connected component contains A, B, C, and D, and the another one contains E, F, G, H, and I. So F, huh, F is an disconnecting set of edges. So this is also called an edge cut. Now the question is this graph two edge connected? So let me write down the question. So question is the above graph two edge connected? So here is the definition. So you can see. So a graph is k edge connected if every disconnecting set has at least k edges. So is this true for k equals to 2?
So for this, we require three edges to be disconnected, na?
Yes.
So it cannot have less than two. Then
Yeah. So is this graph two edge connected?
no, no, no.
No, no. So wait, so I think so that's why I went through this definition. So this is a bit confusing statement. So a graph is k edge connected if every disconnecting set has at least k edges, right? So let me let me say what it means. So a graph is k edge connected is if you remove any k minus 1 or less than k minus 1 edges, the graph remains connected. So this graph is 2 edge connected if we remove any 2 minus 1 edges, the graph remains connected. So is this statement true? So I know that a graph is 2 edge connected. If we remove any 2 minus 1 edges or even less, the graph remains connected. So is this statement true in this graph? If I remove less than 2 edges, any less than 2 edges, is will the graph remain connected?
Yes, if we remove GI, then also it would be connected.
Yeah, right. So no, so this should be true for all set of edges of size less than or equal to 2 minus 1. So in this case, what we are asking is the following. Uh, is if I remove any edge, any one edge from the graph G, will the graph still remain connected? So if you see, so let me,
Yes, if we remove any one, it will be connected.
yes, so let me just try this again. So basically, if I remove, like you said, if I remove any one edge, the graph remains connected. That means it implies that the graph is two edge connected, right? So what about three edge connected? Is this graph three edge connected? So if I remove 3 minus 1 edges, the graph remains connected. Is this true?
No, no, sir.
No, why not?
If we remove AC and AB, then we get disconnected graph.
Yes, okay, so let me in chat, I think someone said. Uh, the answer is yes. No, so the answer is not correct because in this case, what this means is if I remove any two edges, the graph remains connected. This statement is false because if we remove, like he said, AB and AC, then clearly the graph becomes disconnected. That means the graph is not 3H connected, right? Okay. So,
Sir, so where this definition we have written that it is if it is three edge, then three minus one edges we have to
yeah, yeah.
remove.
So, for example, here, I mean, this is a consequence. The definition is this. So, let me put it in the box.
So in this
Huh.
definition, k
So,
minus one is not written. No? That
yeah,
edge
yeah,
minus
yeah, yeah.
one.
No, no, this is what it means, but let me say why this definition, what the definition is saying. So the definition is saying a graph is kh connected if every disconnecting set has at least k edges. So if you see the opposite, a graph is not kh connected. Okay, let me not confuse you, but what it is saying is that, so in this case, so let's go through this definition. So a graph is three edge connected if every disconnecting set has at least three edges. Is this true? Is it true that every disconnecting set in my graph G has at least three edges? No, because like I think someone suggested that there are two edges also. There is a disconnecting set of size 2, so I don't need three edges. So that means it is not true that every disconnecting set has at least three edges. There is a disconnecting set of size less than three edges. So that means the graph is not three edge connected. So this is again, this is just a language difference, but this is what it means. So a graph is k edge connected is if you remove any k minus 1 or less than k minus 1 edges, the graph should remain connected. Then I will say that the graph is k edge connected. This is a definition. I am just changing the language, but what I'm saying and what is written there is equivalent. What I'm saying is easy to, at least for me it is easy to understand, but again, if you want to use this definition or what I am saying, you are free to use it. But anyways, this is the same thing. So for example, like I
So,
said,
let me make it simple.
huh,
If we say graph is k edge connected,
huh,
can we remove k minus one edge? Still it is connected. Then it is true.
yes, so yeah, yeah, so that is what I'm saying. If you remove any k minus 1 edges, not any specific, if you remove any k minus 1 edges or even less is also fine, If the graph still remains connected, then I will say graph is k edge connected. So it's like, if you see, if I have some graph G and somebody said it is uh, 10 edge connected, 20 edge connected, or 100 edge connected, that means the graph is highly connected, right? There are so many edges that even if I remove let's say 90 edges, any 90 edges, the graph still remains connected. That means I can say that graph is 91 edge connected. So this is like what you can say is, how do I measure how connected the graph is, how highly connected the graph is, right? So how do I, so for example, if I look at a person, how do I decide if the person is thin or fat? I assign a weight to that person, right? So if a person is, let's say, 100 or more kg, I say it's fat, he's fat. If it's less than 50, I'll say he's thin. If it's 50, 100, I'll say okay, he's neither fat neither thin. So that means, so in the similar way, I'm attaching a number to a graph G. So a graph is k is connected, that k is a number. Higher the k, higher the connectivity, the graph will be highly connected. And the lower the k, that means there is a small set of edges that if I remove, the graph becomes disconnected, right? So that is the idea here. The higher the k, the highly connected the graph will be, and the lower the k, you can find a disconnecting set of smaller size. Okay. Okay. So for this, sorry, for this graph, what will be the edge connectivity? So what is k prime of G for this graph G? So what is the definition? The edge connectivity of G is the minimum size of a disconnecting set. So what is the minimum size of a disconnecting set in
Two,
this,
sir, two,
graph G?
two. K
2, right?
prime.
Uh, why 2? Because clearly I have found, so we have found basically two edges, removal of which the graph becomes disconnected, because I get this as one connected component and the rest of the things in one connected component. Now if you observe, if we try to find a disconnecting set of edges which contains only one edge, then this is not possible. So if you, I mean, go try and remove only one edge every time, you will see that the graph is connected. Okay. So that means the edge connectivity of this graph is 2. So the answer here is 2. So k prime of G is equals to 2. Okay. Okay. So now let me do some true false kind of questions to make sure that again all this edge connectivity and vertex connectivity is clear. Let me add one page here. Okay. So let's say, let me write down the questions. So give a proof or a counter example for the following statements. Okay, so let's say a free graph with connectivity 4 is too connected. Okay, so here is the statement. I have written it down. So you have to think whether it is true or false. If it is true, you have to provide a proof. If it is false, you have to provide a counter example. And the statement is that every graph with connectivity 4 is too connected. Right? So take your time, take a minute and think. If you think it is true, put +1. If you think it is false, put -1.
Sir, is it the connectivity is regarding edge connectivity?
No, no. I will say edge connectivity in that case. If I say only connectivity, that means I'm talking about vertex connectivity. If I say a graph is k connected, that means I'm talking about vertices. If I say edges, then it will be all about edge connectivity or edge connectedness. Okay. Yes. So you can take a minute, think, and put +-1 accordingly, and then we'll see the correct answer. Okay, I see only two answers, so you can maybe take 30 seconds more and think. Okay, let me see how many of you have attempted. Yes. Okay, so three of you are saying it is true, which is the correct answer. So let me explain why. Uh, okay, so what is the meaning of connectivity 4 here? Okay, so let me show you the definition. So here is the definition. So let me, where is it? Yes, here. So the connectivity of G, written kg, is the minimum size of a vertex cut such that G minus S is disconnected or has only one vertex, right? So here is the definition of connectivity. That means the minimum number of vertices required to delete from graph G to make it disconnected, or I'm left with only one vertex. So that number is called connectivity of G. So here when I say graphs with connectivity 4, what does that mean? So all the graphs where I need to remove at least 4 vertices to make the graph disconnected are the graphs with connectivity 4. So let me write down. So a graph has connectivity 4 if uh, we need to remove at least 4 vertices to get a disconnected graph. Or you can say every vertex cut is of size at least 4, right? Okay, so is this connectivity definition clear? I think somebody asked. Or should I explain it once again? Okay, okay. Uh,
Sir, we can talk about this definition in the form of K-connected graphs. Like that, has a connectivity K if largest K exists, then K is K-connected graph.
so you are saying cage connected graph, right? The definition of cage connected graph.
No, sir, I am saying about vertex connectivity of graph.
Yeah. So I said vertex connected, right? So a graph is so when I say only connected, I'm talking about vertex connected. Okay. So here I'm saying, so if you see the last line here, I'm saying a graph is k connected if its connectivity is at least k. So this is the same as saying a graph is k vertex connected if its connectivity is at least k. So when I'm talking about removing vertices, I don't write vertex connected or vertex connectivity like this, because this is a notation which is followed everywhere. So I don't want to change it here now. But when I say graph is k connected, I'm talking about vertex connected. Okay. uh, okay, so here, like I said, so I'm talking about graphs where every vertex cut is of size at least 4. Now the question is this graph also two connected? Yes, because what is two connected graph? If I remove one edge or less than one edge, the graph remains connected. It is true, because if you remove only one edge, then clearly it will not be a vertex cut. Why? Because I know that vertex cut in this case is of size at least 4. So removing one or less than one vertices uh, cannot disconnect a graph. That means it implies that the graph is two connected. So the graph is two connected, right? Okay, I hope that is clear. Let me give you the next statement. So let's say B. So every three connected graph has connectivity 3. Okay, let me write here connectivity 3. Okay, so the
So
question
can you
is,
say three connectivity? So three connected graph has a degree three. Can we say like this?
three connectivity graph has what do you mean degree of a graph? You need to talk about
Uh,
degree of a vertex, right?
all vertices with minimum of with degree three. All vertices.
Minimum degree,
Yes, yes.
right? Uh, if the connectivity is 3, then minimum degree will be at least 3. Yes, it is true. It is true. Yes, yes. But I'll get to that part. I have one question on that also, which
Sir,
will be I think next one. Yes, yes.
sir, that cannot be possible, I think so. If the minimum degree can be greater than 3 or 4, but a vertex, uh, uh, say a complete graph
Mm-hmm.
and another complete graph,
Mm-hmm.
these two complete graphs merging with one vertex,
Merging with one vertex. Okay.
then if you remove that vertex,
Mm-hmm.
then the connectivity will be 1.
Yes.
It does not depends upon minimum degree.
No, no. What I'm saying is minimum degree is so. This is the relation. So this is what I'm saying. The connectivity of a graph G is at most minimum degree of a graph G.
Yes, at most. Yes, sir.
Yeah, yeah. Yes, yes. Okay, so we'll get back to this part in the next question, but let me just focus on this problem for now. So what I'm saying is, again, take a minute and think whether every three
Sir,
connected graph. Yes.
sir, when it will be equal, you write that less than and equal to.
Uh, okay, let me just get to that part. So what I said is k of g is at most delta of g. Yes. What is your question?
Sir, I am asking that when this is equal to sign is there. You write now.
Oh, are you saying when will this happen?
Yes, sir. Yes, sir.
Let me give you an example when this will occur. Uh, okay, so let's see here. Uh, what is the connectivity of this graph G? Are you asking me characterization like what for what kind of graphs whether this is equal or an example?
Characterization, sir.
Oh, I don't think there is any specific characterization. You just have to look at the graph G and decide what is k of G and delta of G. Yeah, but I don't think there is any like characterization in terms of structure of a graph that you can immediately say these two numbers are equal. You need to look at vertex cuts and say the smallest vertex cut is of size delta G. In that case, these two will be equal. So,
If
uh,
we characterize the graph like that, G is a simple graph, such that delta of G is greater than equal to n minus 2, where n is the number of vertices of graph G.
delta G is greater than or equal to n minus
N
2.
minus 2. And
Then,
G is simple. G is
then,
simple, then we get equal condition.
okay, let me see. Delta G is at least n minus 2. So, if you remove n minus 2 vertices, no, this is still not true. So let me give you an example. So let's take n is equal to 4, I think. So let me see. So if you take this, yes. So, oh wait, no. Delta G is at least n minus 2. The connectivity will be equal to, but this is not a characterization. When I say characterization, I mean if and only if condition. This is a sufficient condition, right? I mean, if this is true, then it will imply this, but just because k of g is equal to delta of g will not imply that minimum degree is at least n minus 2. You see what I'm saying, right?
No, sir, I'm not getting your point, sir.
No, no. So
Can you
what I'm
repeat?
saying is, so your question is, when is it true that k of g is equals to delta of g, right?
Yes,
So
sir.
you are suggesting one condition, which is if that condition is true, like for example, like you said, delta g is at least n minus 2, then it implies k of g is equal to delta g. I'm
Yes, sir.
saying, what about the other way? Whether k of g equal to delta g implies delta g is at least n minus 2, that side is not true. So a characterization is basically if and only if statement. So k of g is equal to delta of g if and only if delta g is at least n minus 2. This statement is not true. This is not a characterization. This is called a sufficient condition. If something is true, then k of g is equal to delta g. This is called a sufficient condition. If as long as this statement is true, the first statement, k of g is equal to delta of g, this is called a sufficient condition. If the other way is also true, if k of g is equal to delta g, then that statement is true. Then I would say that this is a characterization, right? So in this case, if k of g is equal to delta of g, does it imply that delta g is at least n minus 2? Answer is no. I can easily construct an example where k of g is equal to delta of g, but delta g is not n minus 2 and in fact very small, right? So for example, let me give you an example. So actually this only will work, but let me get take a bigger cycle. So if I draw this, so here in this case, can you see that k of g and delta of g are equal? So k of g is also 2 and delta of g is also 2, right? So you need to remove two vertices to make the graph disconnected, and removing one is not enough. So k of g is 2. The minimum degree is also 2 because clearly every vertex has degree 2, so minimum degree is 2. But this does not imply that delta g is greater than or equal to n minus 2, because n here is 2, 3, 4, 5, 6, 7. So delta of g greater than or equal to 5. This doesn't imply that delta g is at least 5. In fact, I have delta g equals to 2.
Yes, sir.
So this is a sufficient condition. You cannot say it is a characterization. Yes. Okay. So let me
It
go back.
it is a sufficient condition is true, no, sir.
Uh, I think yes. So let me give you let me take a minute and think. So until then, you can think about the part B, and I will think about this. Okay. Yes, this is true. Yeah, yeah. This is a sufficient condition. That is true. Okay. So okay. So those of you think B is true, right? B true, or those of you think B is false, right? B false. Uh, until I get at least five responses, I will let you think. Okay. 1, 2, 3, 4. So let me get one more response at least, and then we'll see if this is really true or false. Okay, that is good. Okay, so let's see if this statement is true or false. So let's first focus on what is a three connected graph. Okay, there's one more comment. Oh, okay, yes. So you are answering the question. Yeah, right. So, right. So the answer is false. I'll tell you why. So let's say a graph is three connected graph. So let's say I have a graph which is three connected. What does that mean? It means if I remove two or less than two vertices, the graph will remain connected, right? So so here what I'm saying is a graph which is three connected is basically any graph where if you remove two vertices or less than two, the graph still remains connected. Does that imply I need to remove at least three? Okay, so let me give you an example. So the answer is false. So let's construct an example where the graph is three connected, but the connectivity is not three. Either it will be more, but let's see. So I need to make sure that if I remove two vertices, the graph will remain connected. So something like this. So if I remove these two, so let's see, if I remove these two, P false. Okay, yeah, yeah. So this is true. The answer is false, but let's construct an a counter example where this statement doesn't hold. Okay. So let's see if this is a counter example. If you remove any two vertices, will this graph? Okay. So is this a three connected graph? So here is a question. Is this a three connected graph? Okay, let me remove these three.
No.
Just a second. Okay, so is this a sorry. No, no, so this is a three connected graph, right? So what is the meaning of three connected graph? If I remove two or less than two vertices, any two vertices or less than two vertices, the graph still remains connected. Is the statement true? Can you find a disconnecting set of size 2 here? Right, so the question is clear, right? So the question is that is this a three connected graph? What does it mean when I say a graph is three connected? It means that if I remove two or less than two vertices, the graph becomes disconnected. If this is true, then it will not be a three connected graph. Can you find two or less than two vertices whose removal will disconnect the graph? If you cannot find it, then it is a three connected graph. So let me just num write the names of vertices. So here, let's see. If I remove A and C, the graph remains connected. You can observe B, D, E, F, all of them are in one connected component. If you remove C and D, the graph is still remain connected. A, B, A, F are in the same part. If I remove C, F, E, A, B, D are in the same part. So no matter um, which two vertices we remove, the graph still remains connected, right? So is this statement clear? Is it a three connected graph? The answer is yes. Sorry, somebody said no.
Can we say three connected graph is a graph in which we have to remove three vertices
No, no,
to
no, no,
make
no,
it?
no, 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 no. A k connected graph is a graph where no matter which k minus 1 vertices you remove, the graph still remains connected. So in this case, I'm saying is the graph 3 connected, which means if I remove 2 or less than 2 vertices, the graph still remains connected. And this statement is true for the above graph. This implies that the graph is 3 connected. So when I say k connected, you have to think in terms of k minus 1, k minus 2 like this. So a k connected graph is where if you remove k minus 1 or less than k minus 1 vertices, the graph still remains connected. In that case, I'll call it a k connected graph.
Well, in this, I have one observation.
Huh.
If we say there is a three connected graph, so I am observing that every vertices has minimum degree 3.
Yes, that is true.
So, can there is a direct connection between this connectivity and degrees? This is my
Yeah, yeah.
question.
So that's what I said, right? So the connection is this. So this is a theorem. So a connectivity of a graph G
So,
is
sir,
at most delta
sir,
of G.
now if we see here, the minimum degree is 3, sir.
Yes, yes. So
So,
k
so
of G will
that,
be at
that
most 3.
Yes. So then this
Oh,
is,
okay. So let me construct another graph where the connectivity is 4. So let me construct a bit more dense graph. I think I need a lot of vertices. So let's say 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So let's say everything is connected. Uh, okay. Uh, I think this one will work. Yes. Okay. So let's say this is my graph G. Is this graph 3 connected? Let's get to that part first. Is this graph 3 connected?
yes.
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 Because no matter which two vertices you remove, the answer is always, sorry, the graph will always remain connected. Now, what is the connectivity of this graph? Is it 3 or is it more?
Connectivity is more, sir, in this. More.
Yes, so clearly connectivity is more than 3 because no matter which three vertices you remove, I don't see anywhere the graph becomes disconnected. For example, just to demonstrate, if you remove these three vertices, the graph will remain connected, the left and right hand side through this part or directly through these edges. So in this case, the graph is 3 connected, but the connectivity is at least 4, and I think it will be 6 or more, but anyways, I need to just say that the connectivity is not 3 because the statement said that every 3 connected graph has connectivity 3. This is not true. For this graph, the connectivity is at least 4, right? Is this uh, if this solution is clear, put +1, and if not, then please ask me questions so that I can answer them. Okay, nice. Okay, so let's. You have a question or
Yes, sir.
yes, please ask.
Yes, sir. I'm saying that
Hmm?
a graph is said to be connected
Huh?
if it has a connectivity minimum three or less than at least three.
Yes, that is true. At least three, not equal to three. Yeah, yes, you're right.
Yes, sir. Okay.
Yeah, yeah, that is like what you said is true. Yes. Okay, so let me add a question. So C part, every k connected graph is k edge connected. So take a minute, don't rush. If you think the answer is true, put +1. If you think answer is false, put -1. And let's see after a minute if it is true or false. Okay, so if those of you who think the answer is false, please try to construct a counter example. And if you think it is true, try to construct some proof where, I mean, which will prove the statement. So take a minute and think through.
um, if we make like in the Sylvester's graph, if we make one of it, like
Mhm.
how can I explain it?
Or maybe you can help me draw. How many vertices are there in this graph? What you are saying?
8.
8. Okay. one, two, three, four, five, six, seven, say eight. So let's say one,
Uh,
two, three, four, six, seven, eight. Okay. So which edges do you want me to add?
I want you to add 1 8,
One, eight,
1 2,
one, two,
8 7,
eight, seven,
7 6, and 2 6.
two, six. Okay.
Now you can add 6 uh, 5,
Six. Oh, wait, where is S- six,
6
five,
5,
hmm,
5 4,
five,
4 3, and 3 2.
okay. Hmm.
Like, no, it is a bit different. Such sorry.
Okay.
Uh,
But
Sir,
but
if you take a graph with a bridge, suppose a graph is two connected, when you remove two vertices, but it has a bridge, so
okay.
in the
Let
remove you
me
can
draw.
say,
So is this graph
uh,
fine?
yes,
Okay. Let me write
this
down.
is two connected, but it has a bridge. If you remove one edge, the graph becomes disconnected.
Is this graph two connected? So let me first write that part. Is this graph two connected?
No, sir, it's not too connected.
Yeah. So I think, wait, I didn't see name, but okay. So this graph is in fact not two connected. That is not true, because if you remove, for example, vertex D, then the graph becomes disconnected. So it is not two connected. It's only one connected, and the connectivity is in fact one. So this is not a counter example.
Sir, I'll give an example.
Okay. Let me write. Okay. So how
Two,
many vertices should I put?
sir, two complete graph of any more two of order four.
Okay. So let's say four.
No, 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 no. The second complete graph merging with a single vertex.
Okay. So let me. So two complete graphs with one common vertex, right?
Yes, yes, sir.
Okay. So let's draw. Right? Is this fine?
Yes, sir.
Okay. So for what K are you saying this is a counter example?
It's one connected,
Okay.
and it is edge connectivity is at least three.
No, I'm not talking about edge connectivity. Right? There is a the statement is saying that every K connected graph is K edge connected. So I'm talking about K edge connected. So is this graph one edge connected? Then this will be a counter example. Clearly, this is a one connected graph, but then it is also one edge connected, right?
This is not one edge connected, I think.
One edge connected is basically you are not removing any edge and the graph remains connected, which is true, right? Because this is a connected graph. There is only one connected component.
Yes, sir. Yes, sir.
So this is not a counter example. So in fact, this statement is true. I'll prove it. See, the intuition here is that what is it saying? What is a K connected graph? If I remove K minus 1 or less than K minus 1 vertices, the graph remains connected. That is a K connected graph. If I have such a graph G, and if I remove K minus 1 edges, can the graph becomes disconnected? The answer is no, because um, uh, okay, so let me use the theorem, but this is more intuitive because see, if you remove vertex, it simultaneously removes lot of edges, right? The intuition is that if you remove K minus 1 vertices, you are allowed to remove at least K minus 1 edges and even more, because if you want to delete K minus 1 edges, so let's say, okay, so let me give an example, just a, this is a intuition, I will prove it. So let's say the graph is K connected, but it is not K edge connected. Okay, so let's say you have two connected components, and let's say this, sorry, this is my edge 1, 2, 3, and K minus 1. So let's say the graph was K connected graph, But apparently, just for the sake of argument, it was not kh connected. What does that mean? There exists a disconnecting set of edges of size at most k minus 1. So let's say these are the k minus 1 edges. So if you observe, in that case I will also be able to construct a k minus 1 size vertex cut, because I can just remove these vertices, and then automatically these edges will be removed and these two components will form. So so that's why. But so this is just an intuition, let me prove it. So this is where this theorem from you have learned in your class will help. So let's say we use a theorem. So this is proved in class, so you can see the proof later. So what it says is that if G is a simple graph, then K of G is at most K prime of G at most delta of G. So this is the theorem. There is only, I think, one theorem in this connectivity part of the I mean topic, which says that this is a vertex connectivity. So if the connectivity okay, how do I say this? Uh, if the connectivity of graph is, let's say, k, then the edge connectivity will be at least k, and the minimum degree will be at least k as well. So this is the theorem. So let's see. Um, so let's say I have a k connected graph. Can I say that if a graph is k connected, it implies that k of g is at least k? Is this statement true? So let me add a page, just a second. So I'm saying, so look at the statement in the blue box. I'm saying that a graph is k connected implies, okay, there is one way implication, implies that the connectivity of the graph is at least k. Is this statement true?
Yes,
Yes,
sir.
sir. Yes, sir.
Right, because this is just a definition. That means k of g is at least k. So I can say, sorry, k of g is at least k. Now using this definition, I can say k prime g is also at least k. So it implies that k prime g is at least k. If the connectivity, h connectivity is at least k, so if the h connectivity is at least k, then it implies that the graph is kh connected. Let's look at the statement in this blue box. Is it clear? If the h connectivity of my graph is at least k, then it implies that the graph is kh connected. Why is this true? Well, what is edge connectivity? It is the smallest set of edges I need to remove to make the graph disconnected. If what I need to remove, what the number of edges I need to remove, the smallest number is at least k, that means, what does that mean? That means removing k minus 1 edges cannot disconnect the graph. That means it is k edge connected, right? Take a minute for this blue box, this second blue box, and think. If you have any doubt, please ask. uh, I'll give you a minute. Okay, if this is clear, then also put +1, so that I'm I'll be comfortable to go to the next question then. Okay, okay, I see few +1s. uh, okay, okay, so I hope this is clear. I think this is just a, I mean, this is just a language, right? There is not really any graph theory going on here. It is just saying that the smallest number is k. That means you cannot remove less than k edges and disconnect the graph. And that is the definition of k edge connected. Okay. You can just take a minute and think. It will be clear. So let me go to the next question. Uh, okay. So what about the other way? So let me just rub this and write here only. So actually, no, let me keep it. Let me write here. So let's say D part. What about the other way? Every k edge connected graph is k connected. So right, so this C and D are opposite. Here I proved that k connected graph is k edge connected. Now the statement is every k edge connected graph k connected?
Yes, it is false.
Okay. Okay. Wait. So let the others also think for a minute. Because yeah. Until then, you can try and construct a counterexample on your own for this statement. Every k edge connected graph is not k connected. Okay. Okay. Yeah. I'll wait for a minute.
It is false, sir, false.
Okay. So wait. Let everyone think. Okay. So let me see if anyone wrote it in the chat. Okay, so I don't see any answer till now. Okay, so the answer is correct. You are right. The statement is false. But now, can you give me a counter example for this?
Sir, as
Uh,
you said, edges we have to remove more with respect to vertices.
yeah.
You
But
said.
just because you cannot remove k edges, you can always remove k vertices
So
because that
now,
fits in.
vertex, as you said, is more powerful
Mhm.
than edges. So if they can't be equal.
Yeah. But just to make it a formal solution, can you give me a simple counter example?
Sir, that example which I gave already regarding a complete graph having common vertex.
Okay. Let me draw that example. Let's draw for three only. Okay, so let's look at this. So for what k you think this is a counter example? K is equals to,
More than two.
okay, so
Two
let's
are
take
two.
2. Huh. 2 is
Okay.
also fine. Yes. So this graph is 2 edge connected. Why? Because removing one edge does not disconnect the graph. You can observe this. So if you remove only one edge from this graph G, it doesn't disconnect the graph. But removing one vertex does. So if you remove this C vertex, then you are left with two connected components, this and this. So I can say this graph is not two connected, but it is two edge connected, right? So this is a simple example. Nice. Yes, so this is right. uh, okay. So this was the last question from the connectivity part. If you have any questions, please ask, because now I'll move to this flow network part of the topic, or this course. So if you have any questions, please ask. uh, so let me just get a new page till that point. So
Sir, how this is applied in real world? Like as you said, ki if there is a dense graph, then its connectivity is more. We
yeah,
can.
so see,
So
here's
how
a,
the vertex connectivity is used in real life?
yeah. So see, like you can think of it like this. So let's say you have servers, right? So you can have servers for anything, and you are transferring the data from, let's say, point A to point B to point C, like this. But it could be the case that some of the servers are off for some days for what it is called,
Maintenance.
maintenance. Yeah. So if you can construct a graph with as less edges as possible, because the edges will, let's say, require you to construct poles or some electric lines from one server to the other server. So the sort of intuition in real world is that you have to use as less edges as possible, but at the same time make the graph highly connected, or its connectivity should be high. What happen in that case will be your cost will be low because your edges are low. Again, a this is a real life problem. You need to use minimum number of, let's say, electric lines or something like this, but at the same time you are making sure that the connectivity is high. That means even if 10 servers went for maintenance for a week, the other servers at least can communicate with each other, because removing 10 vertices will not disconnect the graph, because let's say the graph you constructed is 11 vertex connected or 11 edge connected like this, right? So this is, I mean, you can put vertices as anything. I mean, as servers or water supply, electricity supply, or computers or anything, and the edges are just connections. Okay. Yes. Okay. Um, okay. So let's do problems on flow network. So let's see. So let's say questions on flow network. Okay, so let me give you a graph and we'll see what is flow, what property satisfies, what is, so let's say this is A, this is B, this is D, this is C, 6, 8, 5, 2, 1, 2, 4, 2, 6. So, so this is like one of the most important topics in graph theory called flow networks. This has applications in, I mean, numerous number of numerous cases. Okay, so what is the problem here? What are we studying? Okay, so let me explain that. So you have a directed graph G. What do I mean? What do I mean by directed graph? There are directions on the edges. So for example, here the edge between S and A is going from S to A, right? The edge is not A to S, but S to A. Then there is a S to B edge, A to B edge. So basically, it's a directed graph. Okay. Next, I will put what is called a capacity of an edge. Okay. So let me write down these terms. Capacity of an edge. So in the above example, capacity of edge SA is 6. Okay, so you can think of it like this. So there is a vertex S which is called source, right? Source means something which gives out some whatever it is of source of, and then I have a sink which is T. So here S is a source and T is a sink, right? So this is a source, this is a sink, and then you have, like I said, capacities on these edges. What you have to do is you have to construct a flow from S to T. Now what do I mean? So you can think of it like this. So this is just an informal example, okay, just for the understanding. We'll get into formal parts just in a minute. So you can think of it as a water tank or something, a water tower or something, and you and these edges are pipes. Okay, now here is the thing, these pipes, let's say, have different diameters, right? So if I have a big diameter pipe, so let's say bigger diameter, so let's say I have a pipe which has diameter, let's say 6 meter, then it can pass a lot of water compared to a pipe which has diameter only 2, right? So I'm talking about a flow. I will start at S, I will send some water, electricity, traffic, you can think of anything, but in this case just think of it as a number. Some flow is, something is flowing from S to T. So it will start at S, I will say okay, S to A it will go, A to D will go, D to T will go. You have to make sure that the flow or inside a pipe is at most, or it is less than its capacity. So let me give you an example of a flow. and then it will be clear. So let's say you take S, A, B, C, D, and E. So the edges are like this, and these are, let's say, the capacities: 5, 2, 2, 1, 2, 4, 6, 8, 5. Let me denote the flow by red color. So let's say there's 3 flowing from here: 3, 3, 0, 1, 0, 8, 0, 2, 0, 2, 0, 4, 0, 5. So here is a question: is this a valid flow? Can a flow look like this? So I have a graph G, and I'm saying that S is a source and T is a sink, and I am saying that, let's again, this is just a flow. Let me not get into like what kind of flow this is. So the question is that, is this a valid flow? Is this a valid flow network?
So
Yeah.
this is not valid because A and C you have given three, but capacity is two.
Exactly, right. So the first property of a flow network is that flow from any edge u to v should be at least its capacity. So the answer is no. This is not a valid. This is not a valid flow network, right? So this red part here must have been at most two. So let's say two. Okay. So let me give you one more question, and we'll see whether that is a valid flow. So this first property is, I hope this is clear. The flow inside an edge should be at most its capacity. Okay. So let's see: S, A, B, C, D, E. So we have the same capacities: 2, 2, 4, 8, 6, 5. And let me write the flow: 3, 2, 1, 0, 1, 2, 0, 0, 3. Is this a valid flow network?
Yes, yes.
Take your time. Don't be in a hurry.
No, no,
uh,
sir.
okay.
No.
Okay, so some of you are saying yes, some of you are saying no. Let me wait for a minute. Let others also think.
because different flow from S to C, S to T.
Uh, okay. Yeah, so I think what you are saying is right. So let me explain what she's saying. So here is a problem with this particular flow network. If I focus on this vertex C, there's something going on. So let's see what is going on here. The flow, again, whatever it is the amount of flow going inside C is 2 right here, because there is no other incoming edge inside C, right? Because there is only one edge AC. So the amount of flow flowing inside C is 2. Now this is called flow conservation. The amount of flow going inside a node should be equal to the amount of flow leaving that node. But if you see here, the flow leaving C is 1 plus 2. This is 3. So this is incorrect. So this is the second property of flow network. So this is called flow conservation. So what is flow conservation?
Oh, but you have not disclosed this. You said ki flow. So we are thinking about the capacity. Now you said ki conservation, then it is no.
Yeah, yeah, no, no. So what I'm saying is, the
So
question
what?
is, is this
For
a valid
capacity,
flow?
for only if you see the for first property, capacity,
Yeah,
it
yeah,
is
yeah. So capacities
Sorry,
are true. Yeah, yeah.
sir is constructing the definition of flow right now,
Yeah,
I
yeah,
think.
I'm motivating this definition, like why this property should be there. See, because I mean, again, so if 5 megawatt of electricity enters into, I don't know what is called, capacitor or something, the amount of electricity it is leaving should be equal. It doesn't store. So these nodes should not store anything. These are just sort of points or anything. So the amount of flow going inside a node should be equal to the amount of flow which is leaving that node. So let me write down. So this is called a flow conservation property. So
conservation at nodes. That is the correct.
yeah, yeah, yes, yes. So this is called flow conservation for every vertex V except S comma T. So this flow conservation property is need to hold only for vertices which are neither sink nor source, right? So if you see here S is leaving 3, but there is nothing coming in, but that's not a problem because I'm saying S is the source. So we can generate as much flow as we want, but okay, so that is one. And simultaneously, if you look at T, so here it is T, there is only incoming flow, there is no outgoing because it is a sink, it is fine. So this flow conservation property only is valid for all the vertices except S and T. And what is it saying is that summation fu comma v, where u belongs to v of g, is equal to f v comma w, w belongs to v of g. So this first summation denotes the amount of flow going into a vertex, and this is equal to amount of flow leaving, let me say node. I think this is more being a node. Yes. So yeah, so this is a what is it called? This is a flow conservation property. Okay. So now let me ask you a question. So let me take this example only. Let me change some numbers. Okay, so here's a question. So first of all, check whether this is a flow network, a valid flow network. And if you think this is a valid flow network, then calculate the amount of flow from S to T.
No, sir.
So D, in this D, that conservation is not holding. Sir.
Wait, what? D?
D
Uh,
vertex.
D
oh,
conservation
yes,
is
yes,
not.
yes. Yes, yes. So for D, the incoming flow is 2 and the outgoing flow is 3. Okay, so let me draw one more. I think this is also, I hope this is valid. Let's say S, A, B, C, D, and T. Five, two. Okay, so here is a flow network. Check if all the properties of flow are satisfied. If yes, then calculate the amount of flow from S to T.
It is valid, sir, and S2T is 4, 5, sir, 5.
Okay, so let just a minute. Let others also stare it for a while and see this example. So the incoming outgoing is correct, right? So 3, 2, 1, 2 will split into 1, 1, 1, 1, 2 is 4. Yes. Okay. So I hope everybody can see that this is a valid flow network because all the capacities are, I mean, all the flows in the edges are at most the capacities, and also flow conservation properties satisfied. Now let's calculate the flow from S to T. So the definition of flow from S to T is this, or you can even say this. U belongs to V of G. So it is basically saying that the amount of flow leaving S is the amount of flow, or the amount of flow which is going inside the sink, which is T. So let's see how much this is. So this is mod F is equal to F. There are two outgoing edges, F of S comma A and F of S comma B. This is also same as F of C comma T plus F of D comma T. What is F of S comma A? This is 3 plus 2. This is 1 plus 4. So this is 5. This is also 5. So this is a flow from S to T between S and T. Okay, is this clear how I calculated the amount of flow? So you basically just look at, so you first verify this is a correct flow network, whether these properties of flow are satisfied. Uh, Once you that is done, you calculate the amount of flow leaving S, or you can calculate the amount of flow going inside T, which is 5 here. Okay. Uh, okay, I hope that is clear. Um,
Yes, sir.
okay, so let me ask you this question. Um, okay, so you have a question?
Yes, sir. Is there any technique to draw a floor which is valid in a graph?
No, I mean flow it will be given to you, or you can construct it by hand. So see, these are just numbers you have to put next to its capacities, and no matter which numbers you put, you just have to make sure that uh, the flow should be inside every edge should be at most its capacity, and flow conservation properties should be satisfied. If these two properties are satisfied, you can say it is a valid flow network. uh, is that your question, or something
No,
else?
sir. I am asking that you drawn a flow network
Mhm,
in a question. If you shown that, and
mhm.
then how you draw? I am asking, just asking that.
Oh, this is, see, so okay, so let's try to draw one more flow. So okay, so this is my next question, and that will, I think, answer your question also. uh, Here in this case, I calculated a flow, I mean, I have drew this red numbers which shows a flow from S to T, which is of size 5. Can you draw yourself a flow of size 6? Right, so let me just okay, let me just take this graph here, just a minute. uh, so okay, so let's come here. So this is a flow of size 5. Question: can you construct a flow of size 6 on your own? So take a pen and paper, think about it, and try to construct a flow of size 6, and then we will do it together after a couple of minutes.
Okay.
Yeah, yeah. So take a minute and try to draw, and then we'll all of us will take a look.
In the same graph, we can change the flow values.
Yes, yes, but just a minute. Let everyone try, and then we'll see. Yeah. So let me add an edge here. Okay. So okay, there's some chat. Okay, I think one of you is done. So let's draw it together and see. So let me just draw the same graph again. Okay, let me just copy paste it. Okay, so let me remove these flow values, and you can suggest what flow value should I put so that the flow becomes 6.
So
So I have
first,
put the old, just a second,
essay you can do, sir, 4.
just a minute, let me just correct. Yes, so what about SA? How much?
4, 4.
Okay.
SB you can take 2.
Okay. What about AB?
AB is 1.
AB is 1. Okay.
Then AC is 2.
Okay.
AD is 1.
AD is 1.
BD is 3.
Okay.
Then T is 4.
Hmm.
Then ED is 1.
ED. You mean CD?
CD.
CD is 1. Okay.
And then CT is 2.
Okay. So let's see if this is a valid flow network. Um, what do you guys think? Is this correct? So capital C.
DT must be 5. DT
Yes,
must be
yes.
5.
Okay. Yeah. So you are right. So there is a small flaw. So for D, the incoming is 5, 3 plus 1 plus 1. But I think you said 4 by mistake. So let me just say 5. Yes. Okay. Is this a valid flow network?
No, sir. C
No,
vertex.
sir.
Okay. There is a problem at C vertex now. So there is 2 coming in,
So to
but
1, now you have to reduce 1 there.
CT is 1. Okay.
CT is 1.
Okay. Now let me see. For C it is 2 2, then it's 5 5 is 4 2 1 1 2 1 3 3 1 1 5. Yes. So you are right. So this is a flow of size 6. Okay, now the question is, can you draw a flow of size 7? Just take a minute and think, can you draw a flow of size 7?
Yes, 7 is also possible.
No, not possible.
S- Okay, so let's see. If you think it is possible, what things you would want me to change here?
It is not possible because if you change it as 5 from S to A,
Huh.
then outcome from A cannot be.
You can change AB, right?
Problem at D vertex, sir.
Yeah, yes, yes.
Yeah.
So let me save some time. I think I am running low on time. So you are right. There is no. flow of size 7. uh, Now, so this is, I think this is something you will see in your next few classes. So the objective, given a graph G, given a directed graph G with capacities, the objective is to find a maximum flow. How can you construct a maximum amount of flow from S to T? Okay. Now, let me only do the part which is done till week 6, just to make sure that you are not going ahead of the course. So let me just say this. So okay, so this is right. So this is a flow of size 6. Let me what should I do? So let me rub this for now. Okay, so let's come back and look at this flow of size 5 here. So in this case, I had a flow of size 5. Now you will see in the coming lectures, you will use this idea of called augmenting path technique to calculate the maximum flow. Okay, so now let me first only define how you construct a augmenting path of a flow network. So for example, so if you can see, let me just show this here.
So
So
this augmenting path is different from what we have
yeah,
learned
yeah, yeah,
earlier.
yes, yes,
So
yes,
why we
yes.
have made the name same? So it is confusing.
uh I don't know, this is just a notation. I mean, you can call any, but see, this is, that was in terms of matching, and this is in terms of uh, flow network. But see, the reason these two are called augmenting path, the reason comes from algorithms. So, so if you see, I mean, this is not a algorithms course, but uh, the way you construct maximum matching in a graph G is to find augmenting path again and again and again and again until you get a maximum matching, right? So you construct a matching, you find the augmenting path, you increase the size of matching, again you calculate the augmenting path, again you increase the size of matching, you go to the point where you have maximum matching. The same thing will happen here, as you will see in your coming class, in few classes, which is that you will have given a flow network, right? So something like this. So I have drawn here one network. Now again, you will ask to calculate a augmenting path inside a residual network. I will define what are these in this case. And what you will see is that the algorithm you will learn in coming classes will be something like this. You will draw a flow of size 1 to whatever it is, and then you will ask whether this is a maximum flow. How do you check whether this is a maximum flow? You will construct a augmenting path, which I will say what it is. If you can construct a augmenting path, you will be able to increase the flow, right? So if your flow was 5, I was able to construct a flow of size 6. Now the same question asks, we can ask the same question, can I increase the flow from 6 to 7? The answer was no here, because you will see that you won't be able to construct a augmenting path. So this augmenting path is a technique from algorithms. By repetitively calculating augmenting path, you are going towards solution step by step. You are increasing the size of flow. In the matching, you are increasing the size of matching, so that eventually you'll go to the maximum matching. Here in this case, you will again and again find augmenting path, so that you will be able to increase the flow from 5 to 6, 6 to 7, 7 to 8, whatever it is. And eventually, once there is no augmenting path left, you will be able to get a maximum flow. Okay, so this is the reason why these two names are same. But let me just define what is residual network and augmenting path in this context of flow networks. Okay, so okay, uh, wait, was that clear what I said at least?
Yes, yes, yes.
Yeah,
In terms of algorithm, it is coming up. Yes,
yeah,
but
yeah. So once you will see the algorithm in next few classes, you will realize what I'm saying. But for now, let me define residual network. So how do I define residual network? Okay, so residual network is defined for a flow network. So let's say this is my flow network. I have given some flow. So the red values define flow and the black values are capacity. So let me explain how you define a residual network first. So you go to S. So you draw the same graph, same vertices. Okay. So you stop here. You first draw the vertices. Next, what you do is the following. Now you look at the flow from S to A. It is 3. So what you do is you reverse the edge from A to S and give weight 3. Okay, this is the first step. So every time you have a flow from U to V, you reverse the edge V to U and give it the weight 3. Okay, the flow is now capacity of edge A to S. Okay, now I will draw one more edge from S to A. What this edge will have capacity of S comma A minus flow of S comma A, which is 2. Right, so is this clear what I did for SA? I had a flow from S to A of size 3. What I did first is I reversed the edge from A to S, and now the flow 3 which I had in the flow network is now capacity of edge A to S, and I also draw S to A edge, and the capacity will be the new capacity of S to A will be capacity of S comma A minus capacity, sorry, flow of S comma A, and you repeat. So A to C.
Sir, we can see also that as A is 3 and reverse is 2,
So, sorry, I didn't understand. Can you
we
repeat?
can say from S to A is 3
No, no,
and
no,
reverse is 2.
no. So this is the definition of residual network. No, no, you cannot say that. You will see why. Just for now, let's stick to this one. I'll get to you. So let's do this for every edge. So A to C, there was a flow of size 2. So I will reverse the edge, put capacity 2, and in the forward part, I will put capacity is equal to capacity of A comma C minus flow of A comma C, which was 0. Right? So you repeat. Uh, S to, I'll go from B to S, and the capacity will be 2, and in this side it is 0. uh, Reverse it is 2, forward it is 2. From D to T you put the old edge in the opposite direction, so here it is 1. Here I have 0 flow, so in the backward direction it will be 2, and it will remain 0 here. Oh no, wait, I wrote something wrong. I meant here, the flow here to here is 0, so the flow from here to here, so the capacity will be 0, and here it will be 2. And then I have flow from A to D, so I'll draw an edge from D to A with capacity 1, and this edge will have capacity 0. Then I have flow from C to D, so I'll draw an edge from D to C, and the capacity will be 1 because the flow was of size 1, and then it will be 7, 8 minus 1. Here T to C, it will be how much? 1, and in the forward part it will be 5. Okay, so this is the residual network for this flow given above. So is this definition clear how I constructed this flow network? If yes, put +1 so that I'll explain the next part quickly.
So direction of AB is reverse, I believe.
AB, no. So because if you see the amount of flow from A to B was 0, so the capacity of B to A will be now 0, and then A to B will be 2. Right, so what I'm saying, if you have, so let's say you have edge U B with flow F and capacity C. So let's say, oh, let me draw here, it will be easier for you to see. So let's say you had this edge V with capacity C, and let's say flow was F. What this will convert here to the following diagram: U B, the flow was F, so I'll put an edge in the reverse direction with capacity F, and then in the forward direction I will put C minus F. Right, so this is a
Um, I wanted to ask that in A to C, we have to take into account that the capacity is always greater than the function f, flow, right?
Mhm.
So in A to C, it has to be strictly greater than that, right? So in A to C, we shouldn't be having a forward. Uh,
Wait. This is in this residual network, there is no flow. this is these are all capacities of edges. So from C
okay,
to
okay,
A
okay,
I have edge 2, and A to C I have edge, but these numbers are capacities. Okay.
okay, okay, okay,
Yeah,
okay.
yes. Now, what is a augmenting path in a residual network? Okay, so this is a residual network. Again, why do I calculate a residual network? Why do I am calculating augmenting path? Will be clear through your next classes, because this is an algorithm. So you have a flow here, you drew a flow. For that flow you constructed a residual network. Now for that residual network you construct what is called augmenting path. Augmenting path. Okay. So what is an augmenting path? It is just a path from S to T. Okay, where you have a path from S to T whose capacity is at least one in each edge. While going from S to T, I will use this directed edges, and I have to see if path there is a path from S to T such that every edge on that path has capacity at least one. So can you see, is there a path from S to T such that, so this is a directed path. Okay, you cannot use the reverse edges. That is one. Is there a directed path from S to T so that each edge has capacity at least one on that path? Okay.
Yes, yes.
Okay, so can you give me the path?
S to A,
Just a second. So just S to A. Okay.
A to B,
A to B.
B to D,
B to D. Okay.
and D.
Yes, D to A. Okay. Now let's let me show you the magic now. What happens by calculating this augmenting path? So let's this fits. Okay, I hope so everything fits here. So what I did, wait, hello, am I audible?
Yes,
Yes,
yes.
sir.
Oh, okay, I thought I got disconnected. Okay, so let's see the importance of augmenting path. So I calculated this augmenting path in my residual network. Now how do I exploit this? How do I use this randomly defined augmenting path? Here is what you can do. You go to your flow network. So I'm now looking at this part. Okay, the first flow network, and along the path that I have found I will increase the flow by 1. Okay, so what I'll do is this. So let me take the red color. In the augmenting path I was going from S to A. What I will do is I will increase the flow by 1. So in the flow will now be 3 plus 1. Okay, then I went from A to B. Now the flow will be 1 plus 0. I went from B to D, the flow will be 1 plus 2. And then I went from D to D, D to T, the flow is 1 plus 4. Now, can you check whether this new flow is still a valid flow network? Take a minute and think. What I did is I had some flow. Okay, my goal is to count a maximum flow. So what I did is I looked at this augmenting path which I calculated, and along that path, I increased the flow of each edge by 1. Now, can you see that this is still a valid flow network,
Yes, sir.
right? I mean, take your
Yes.
time. This is just a checking. Now, see what did I do? I had a flow of size 5. I calculated its residual network. That is the step 1. So this is step 1. I looked at the residual network, and in step 2, I calculated this augmenting path from S to T. I went back to this, so this is step 3. I went back to my flow network and I was able to increase the flow by 1. Now I have a flow of size 6. Now, so you see what happened here? Every time I have a flow network, you will have some flow. So one might ask, okay, this is a flow, but I'm interested in a flow of larger size. Can you construct a larger size flow? How will you do that? Here is how you will do it. You will take that flow network, you will construct its residual network. That is step 1. You calculate the residual network, which is basically changing each edge and its capacity like this. So I have drew here step 1. Then inside this residual network, you are looking for a augmenting path. What is an augmenting path? It's just a directed path from S to T, such that every edge on that path has capacity at least 1. Let's verify. S to A, I had capacity 2, so I'm okay. A to B, I have capacity 2. B to D, I have capacity 2. D to T, I have capacity D. So this is the augmenting path. Step 3, you go back to your uh, uh, flow network and you increase the flow by 1 on each edge along that path. Now you have a larger flow and you repeat. This is a algorithm. This is the algorithm basically. You take flow network, you calculate residual network, you calculate augmenting path, you go back to your flow network, increase the flow. Repeat, repeat, repeat. Repeat this process until you cannot get a augmenting path. Okay. So give me 1 minute. Let's together draw a residual network for this graph, and you will quickly see that there is no augmenting path, which means the flow of size 6 is in fact a maximum flow. Okay, just a minute. Let me just quickly draw it. Uh,
You will make the augmenting path with the increased one, right? Like,
Only one. Yes, yes. I increase the flow by only one.
yes.
Okay. Oh, so let me just draw this quickly. I think I'm already out of time, but okay, so let's see. So I had capacity in reverse direction will be 4 because S2A I have flow 4 and this will be 1, and I have these two edges. The flow in the reverse direction will be 2 and here it will be 0. I had a flow of size 1, so capacity in the reverse direction will be 1, so this is 1. uh, this will be 2, this will be 0, the reverse will be 1, so this will be 5, this will be 1, this will be 7, this will be, sorry, this will be 5, this will be 0, 3, 1, 1, 0. Wait, class चल रहा है रुक जा. So see, this is a residual network for this new flow. Now my question is there a augmenting path in this residual network? Can you find a augmenting path in the residual network?
No, no.
No. You can just observe, you can go from S to A only because you cannot go from S to B, the capacity is 0. Then you can only go from A to B because A to C is 0. Then from B you can go to D because you can go because the capacity is 1. You cannot go from D to T because your uh, capacity is 0, but you can go from D to C and C to T. Let me think. Can you increase the flow here actually? So if you make it 5, you can make 2, make it 4, you can make 2. Oh, you can even increase the flow. See, so this is the idea. uh, yes, so let's see. So this is again, let me just quickly add the flow. In fact, your 6 was also not enough because I was able to find, uh, let's see, so here, 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 here. Now you can even increase the flow. So 1 plus 1 plus 1 plus, uh, wait, I think I drew something wrong or what. So I increased here. I go from D to C with 1. What did I do wrong here? Before went from S to A, then A to B, then B to D. Yes, yes. So when you are going the other way around, right? So here, uh, the edge is from D to C. So you decrease the flow if the direction is opposite, right? So you in fact do -1. So you do, sorry, you do -1 here, and then from C to T you put +1, right? So let's see if this is a valid flow network. Let's verify. uh, Flow is 5 here, capacity 5, 2 2 2 2 4 4 1 1 2 2 2 6 0 8 5 5. So this is fine, right? Capacities are more. Now let's verify the flow conservation. So 5 in, 2 plus 1 plus 2. So this is 5. Sorry. Yes, you're right. For B, incoming is 2, 2, outgoing is flow. Then for D, incoming is 1 and 4, outgoing is 1 plus 4. For C, incoming is 2, outgoing is 2. So yes. Uh, so see here, in fact, I was able to find a flow of size 7. Uh, did you see
No,
how
no,
did?
but sir, how can you
Hmm? Yeah, yeah, please ask.
reverse reverse flow is possible? Minus
No, no,
one.
so that's what I'm saying. How do I use the augmenting path to calculate or to increase the flow? So while I'm going along that direction inside residual network, so I went from S to A, I had an edge. From A to B, I had an edge. From B to D, I had an edge. So I was doing +1, +1, +1. When you go in the opposite direction in the residual network, you do -1, right? From D to T, I went in residual network in the augmenting path, but the edge inside flow network is C to D. So, so this is like increasing the flow by -1 because the direction is opposite, right?
But sir, my question is, can we go direction opposite because
No, no, no,
we
no.
are
I'm
dealing
not.
with direction, we are
No,
dealing
no.
with a directive graph.
Yes, yes, yes. But see, I'm not really going in that direction. I'm just putting +-1. I'm just increasing the flow and decreasing the flow on some edges. See,
Okay,
I'm not
okay,
saying,
understood.
yeah, yeah,
Understood.
yeah,
We are
yeah.
reducing one to zero. That's all.
Yes, yes, yes. In the augmenting path, you can go because I have edges in the opposite direction, but in the flow, you cannot go. You're right. Now, I was able to construct a flow of size 7. Now, okay, so I'm already out of time. What you can do is take your time uh, when you are free and try to draw a residual network of this graph in where I have flow is equal to 7. You will see that once you draw a residual network and try to calculate a augmenting path, there will be none. You won't be able to find a augmenting path because 7 is maximum as far as I think. I don't think you can get more than 7. And if and in the case where you if the flow is 8, then you will be able to find a augmenting path. So this is the so let me just summarize here. So you take a flow, calculate uh, what is it called, residual network, then you calculate augmenting path. This only if it exists. It may be the case that it doesn't exist. In this case, if it exists, you increase the flow by +1. So this is a loop, right? So this is the algorithm. I think you will see in your next class only. But let me just tell you here. You start with the flow, you calculate the residual network, you calculate the augmenting path, you increase the flow. You keep on. So this is an iteration of algorithm. You keep on going until this stops here. So until one point, you won't be able to find the augmenting path. And then in that case, you return this is a maximum flow, right? So this in this way, you calculate the max flow. Okay. Okay. So I hope this is clear.
Yes, sir.
If you have any doubt, please ask. Uh, okay. Thank you.
Sir, sir, one small question, sir. Why we say graph theory, sir? Why it is not a applied maths?
No, see, applied maths. I mean, see, when you are doing, when I say we are doing math, you abstract the structure out in the sense that when you study graph theory, you are not really studying flow of electricity, flow of water, flow of traffic, anything. You are just using vertices and edges. So this is called abstract structure. There are many problems in the world which can be what is it called, mapped to graph theory. I mean, graph theory does come under applied mathematics, okay, but the real use of graph theory is when you are doing algorithms, and then it will come under applied mathematics. You cannot really just learn graph theory and use it in your day to day life, or whatever in your engineering or any questions in life. But once you learn the algorithms, then you will see how, the real power of graph theory. Right now, this may look like only a theory and something this which only you're written in books and not applied. This will be applicable almost everywhere, but only once you learn the algorithms part. Okay. Okay. I think is there a question?
Yes, sir.
Yeah, you can ask.
Sir, I'm asking that you drawn a residual network, sir.
Yes. So here, let me go. Yes.
The arrow direction you used is right or no?
The arrow direction is, sorry. Yeah, yeah. So the definition of residual network I explained, right? So you reverse the age and convert flow into capacity, and again you put the main age and write capacity as capacity minus flow. So this is just a definition. You put arrows in both parts in residual network. Okay.
Okay.
Yeah, so this is the definition. I'm not sure if you will see the proof of the algorithm, the correctness proof, I mean why the algorithm works. That also comes under, I mean, I don't know if you learn this, but the reason why we do this is to, again, this is all embedded in finding the augmenting path, but let's not go there. For now you can just take it as a definition how to calculate residual network. Okay. uh, yes. I don't see any questions. uh, yes.
And sir, what's the meaning of flow to be symmetric?
Skew symmetry is basically just saying that if I have a flow of size 2 from A to C, then I just say that I have a flow of size minus 2 from C to A. So it's like saying, see, if the water is flowing from A to B, how much water will go in 10 seconds? Let's say it is flowing 5 liters per second. So after 1 second, I have 5 liters from A to B. So it is same as saying I have minus 5 from B to A. I mean, this is just a, I mean, you don't have to worry about skew symmetry. It is just to, uh, I mean, make it more formal and concrete, so that when I say I have a flow from A to C, it is equivalent to say I have negative flow from C to A. So like this is something like if I have to give you 5 rupees, then you are plus 5. But I mean, how do I say this? It's like saying I'm losing 5, so I'm minus 5 and you are plus 5. So it's just the plus minus signs. There's nothing to, I mean, there is nothing deep, anything about it, I think.
Okay.
Yeah. Okay. So I think I'm already 15 minutes
Thank you,
over.
sir. Thank
Yeah.
you.
Okay. So bye,
Thank you.
everyone. Yeah. Okay. Okay. Thank you.
Thank you.